Here's how to understand centripetal acceleration in physics. So a lot of times you'll be given some sort of roller coaster problem, such as this one, where an 80-kilogram person is on a roller coaster traveling at 32 meters per second at the bottom of a 20-meter radius loop, and we're asked to determine the normal force on the person at both the bottom and the top of the loop. The first thing we need to learn when doing this type of problem is how centripetal acceleration works. Let's say we have a car moving in a circle at a constant speed. If we remember from before that acceleration is equal to the change in velocity over the change in time, you may be tempted to say that since the speed is constant here, that there is no acceleration. However, we have to be careful and remember that velocity has both a magnitude, which is the speed, and direction. In this case, the direction of the car is always changing as it goes around in a circle, which means that the velocity is changing and gives rise to what we call centripetal acceleration. If we wanted a value for this centripetal acceleration, we're going to use this formula, where AC is equal to the velocity squared divided by the radius of the circular path. Looking at the direction of this acceleration, we need to think about where the velocity is changing as it moves around the circle. In this case, we see that the velocity is always trying to be pulled towards the center of the circle, so we say that centripetal acceleration points directly inwards towards the center of rotation. Another cool thing about having an acceleration is that from F equals ma, there must also be a net force in the same direction. In the case of the moving car, it's the force of friction between the road and the tires that keeps it moving in a circle. Whereas with the roller coaster, it's the normal force from the track that pushes on the person, and this is how heavy they feel. So in our roller coaster problem, we're going to start at the bottom by drawing a force diagram. Here we have the force of gravity pointing down, and the normal force from the track pointing up. The next step is to draw the direction of the acceleration, which since it points towards the center of the circle, is directly up, and will have a value of v squared over r, where v is our 32 meters per second at the bottom. Now all we have to do is write out our sum of the forces as equal to the mass times acceleration, plug in the numbers, and after doing a little algebra, we will get the normal force is equal to 4,880 newtons. If we then divide this normal force by 9.8, this gives us an apparent weight of 498 kilograms, which is much heavier than our original 80 kilograms. Now looking to find the normal force at the top of the roller coaster, we're going to need to find the velocity. If we remember from before, we can use conservation of energy to equate the total energy at the bottom of the roller coaster to the total energy at the top. This means that some of our kinetic energy from the bottom will be converted to potential energy when it reaches the top. If we set up our equations and do a little math, this gives us a velocity of 15.5 meters per second at the top. Now drawing our force diagram at the top, we're going to have the same force of gravity pointing down, but now the normal force from the track also points down. If we draw an arrow for the acceleration, we see that pointing to the center of the circle also points in the negative direction. So when writing out our sum of forces is equal to the mass times acceleration, everything will be negative. Plugging in v squared over r with our new velocity of 15.5 and doing a little algebra, we're able to solve for the normal force, which is 177 newtons. Dividing by 9.8, this gives us an apparent weight of only 18 kilograms, which is much lighter than our original 80 kilograms. This is why you feel kind of weightless at the top of a roller coaster. It's also important to note here that whatever speed causes the normal force to be 0 is the minimum speed needed to keep the person from falling out of their seat. And there you have it. That's how to understand centripetal acceleration.